to focus on functions, and some of this will be kind of familiar, and look at probably some new concepts related to functions. We're going to write, one or two proofs probably. So that'll be nice. But it'll be a nice, it'll be like regular old algebra, right? So not the Boolean stuff, just like the algebra that we know and love will come in handy here. Okay. So in this chapter, we're looking at relations and functions. As it happens, every function is a relation. Not every relation is a function. We're going to start on the narrower set of looking at functions. And just broadly, it defines sort of a relationship between two quantities, but that's not quite narrow enough. That's not quite precise enough to define what a function is. A function is really like a machine that maps certain inputs to certain outputs. In fact, the term mapping is synonymous with function. And you have some set over here, A, I'll call that set A, which we call the domain. And then what the function does is it takes domain elements and maps them to some other set over here, which we call the codomain. So I'll call this function f. So what it does is maybe I've got some elements here. And it just tells me like, oh, okay, if I send it through the f function, where do we end up? There's f of a1. So a is an element, a1 is an element of a, f of a1 is going to be an element of b in the codomain. And maybe a3 maps here to f of a3. A2, maybe A2 maps to the same element as A3. That's okay. It's still a function. What makes something a function is that a single domain element can only go to one codomain element. It is okay if two domain elements go to the same codomain element. That's okay. You can double up on outputs, but you can't split your inputs, right? You can't say, oh, sometimes A1 goes to this element here and sometimes A1 goes to this one. That leads to ambiguity into what will come out. Yeah.
What if it's not like, oh, sometimes it goes to this one, sometimes it goes to this one, but like it goes to both. Like when you
but that's the same thing.
It's the same thing.
That's the same thing.
Okay. So like with like square roots and stuff, when you get both a negative and a positive.
Yeah, that's not a function.
Okay.
Yeah. Because there can be no ambiguity. If I plug in something and I say, what's the output? And you say, well, it's either this or this. Like, not a function. It defines a relation. Okay. Like, and that could still be a useful equation. Yeah. But it's just technically not a function. Okay. All right. My favorite, does anybody know what my favorite example of a function is?
No.
No? No one?
You've told me before, but I can't remember.
It's the snack machine out there. You punch in a code and it gives you a snack, okay? So like, if you punch in A1, it'll spit out Doritos, right? And if I go 5 minutes later, I punch in A1, it'll still spit out Doritos, right? If the machine works, you mean if it doesn't like hold on to it, yeah. But then Donna will give you your money back and you can try again. And you just keep putting money in and hope that maybe eventually it'll spit out like 5 bags of Doritos. But the idea is that like when you put in A1, you can count on it giving you Doritos every time, right? And now it is perfectly acceptable to have 2 rows of Doritos. It's okay for A1 and A3 to both give you Doritos. That's 2 inputs going to the same output. What is not okay is to have like Doritos and Cheetos and Twizzlers in the same row. That's like A1 goes, what am I going to get when I punch in A1? I don't know. That's unacceptable. That's not a function. What?
Sounds like a great idea.
Oh man, that's awful. It's like a roulette kind of.
I don't know what I want. Let's just see what it gives me.
Yeah.
It's great for.
Or that's like the I'm feeling lucky like Google search button, you know? But like that would be acceptable if it was understood that there's like one button that doesn't work. But my point is that it wouldn't be a function, right? Okay. Okay, so most of the functions that we work with, we're going to plug in numbers and get out numbers. So we map from the domain into some set called the codomain. If I look at all the possible outputs, like all the elements of the codomain that end up being output elements from the function, we call that the range of the function, or also called the image of the function. The range is always contained in the codomain. It doesn't have to be equal to the codomain. Like if we look at the function like y equals x squared or f of x equals x squared, if I think of this as a function that maps reals to reals, right? All real numbers to all real numbers. The domain is all real numbers, right? I can square any real number I want. But when I square a real number, what types of outputs do I get?
Also real numbers.
What?
Also real numbers, but they're like,
Do I get all of them?
no.
No. What kinds?
Positive?
Yeah, non-negative, right? All the positives and zero, because you could square zero. So here's an example where the range is not equal to the codomain, right? Like the range is all the non-negative real numbers, which is contained in the codomain, but they're not equal. Now I could always define the function and say, I'm going to define this function to map from the reals into the non-negative reals. And then by artificially kind of restricting that codomain, I could say, oh, then the range is the same. But generally, like they don't have to be the same. There is that containment relationship. So let's suppose let's look at this function. So here we've got the function f of x is 2x, you know, and we're mapping each element of the integers to twice its value. So we are very specifically saying that we're mapping from the integers, where we want this to be a function where we just plug in integers. So the domain is integers. The codomain, if I double an integer, I'm still going to be sending into the set of integers, right? So the codomain is all integers. But what's the range? If I double integers, I'm only allowing myself to plug in integers, right? The whole numbers, positive, negative whole numbers, and I double them. Is my range going to be all integers? No. What will my range consist of?
Even is.
The even integers, yeah. So we would say that we write that as 2z, so like all the multiples of 2, right? Like minus 6. When we say that we want to map each element of the integers to twice its value, and we list the domain as z, and what's the codomain? That's also z. We kind of a shorthand when we're defining a function is to define a function. We call it f, and then we use a little colon from z to z. So this is often a way that people will indicate what their domain and codomain are for a function. Let's look at a different function. In example 4.2, we're going to define the function g that maps from r to r, the real numbers to the real numbers, by g of x is equal to 2x. It's going to map each real number to twice its value. Now that looks pretty familiar, right? But how is this function different from the one that we just looked at?
We're allowing decimals.
Right, yeah. I mean, so the function does the same thing, but the function acts on a different set,
Yeah.
right? So the domain and codomain are different in this case. So we'll just note, right, these functions do the same thing, and we would say that the function values, which are the same as the outputs, agree on the integers, because the integers are contained in the reals, right? So G also acts on the integers, but it acts on more, right? A bigger set. So the function values agree on the integers. But, for example, G of 0.5 is equal to 1, right? Because G is the one that acts on all reals. Whereas F of 0.5 does not exist. Because we didn't define it to work on non-integer values. If I look at this notation up here, oh yeah, actually we used it right here. We said that we defined the function g from r to r by g of x is equal to 2x. Another way that you might sort of see this written out is by saying g maps from r to r by mapping x to 2x. And it's the same thing. I mean, it kind of, if you see that notation, I think it seems pretty clear like what they're trying to say. They just sort of wrote it without the function like g of x notation. Okay. Okay, great. Questions before we do some more?
Is that wherein?
Whereas.
Oh. I know it sounds like that.
Okay, so next, let's say we want to define a mapping, which is a function from each non-negative real number x to a real number y, so that y squared is equal to x. And then we want to know, why is this not a function? So I guess I might start this problem by trying to figure out, well, could it be a function? Like, if it were a function, what would that mean? So, to see if it is a function. Let's try writing this out as an equation and then solving for y. Or they gave us the equation. We'll solve for y. So it was y squared equals x. Now this is something that Xavier brought up earlier, but if we want to solve for y, we have to take the square root. Anytime we are the ones imposing a square root on an equation, right, it's not there to begin with, but we're putting it there ourselves, we need a plus or minus. So in fact, y is plus or minus the square root of x. So there's ambiguity. This gives two possible outputs for every value, for every non-zero value for x. That means it's not a function. One thing that if I'm kind of playing around with an equation, or how they're whether they give us the equation or they give it to us as a statement, and I have to find the equation myself, or trying to figure out if it's a function. Sometimes I just try to work with an example. Let's find y if x is equal to 4. And, I'm starting with the equation they gave us. So y squared equals 4. And if I want to solve this, I have to take the square root. And I'm looking to figure out what values do I square to get 4. And, of course, that's plus or minus 2. We get two different outputs. The way that we might sort of think of this in a mapping language is to say that, 4 maps to 2 or -2, right? And then we got these two outputs, not a function. What we should be clear about is that we're saying that this doesn't define y as a function of x, right? And usually when we're working with writing out equations to define functions, we default to x being what we call the independent variable, right, and y being the output. X is our inputs, y is our outputs. But this certainly would define x as a function of y, you know, if I want to kind of reverse the roles of domain variable and codomain variable. Let's do another one. Let's write an expression for the function that sends each real number x to the square of itself plus 1. So they're saying that it sends each real number x. So they're telling us right off that the domain is all real numbers. And then we'll think about what the codomain is in a second. But what is f of x? Like, where does it send x as an expression? Yep, so what does that look like?
F squared plus 1.
Yeah, x squared plus 1. So if I take a real number and I square it, I still have a real number. If I take a real number and I add 1, I still have a real number. So this function f maps reals to reals. The codomain is reals. What is the range of this function? Like, we know that we're going to get real numbers, but can we get all of them? Are we restricted into the type of values that we will actually attain in this function? Positives at least, okay. Still going to be a positive. So, what's that? No, it doesn't. In fact, it doesn't have to be just integers, right? I could get pi as a result, I think.
You're restricted to it being more than or equal to 1.
Yeah. So the f of x values are greater than or equal to 1. Because, you know, the x squared part, that's at least 0, right? And then we're adding 1 to that. So here's the range expressed as an inequality. Sometimes you'll also see the range expressed as an interval, and in which case we start with the lower bound, and then there's no upper bound, so it goes up to infinity. We use the hard bracket there because it's an or equal to 1. If it was strictly greater than 1, we'd use the soft parentheses. Okay, so now look, they've given us a couple of functions. F maps from reals to reals, G maps from reals to reals, and some nice, just good old-fashioned equations, algebraic expressions. Who loves algebra so much now that it's not Boolean? Got a couple hands going up. Good. I mean, I like Boolean algebra, though. So, and we're just going to do a little practice with function notation. I bet you've seen this before, so this might be a little bit of review, but f of 2 just means tell me what your output is when you plug 2 into the f function. So if we think about this function, here's our f of x function, 7 minus 2x. So 7 minus 2 times the input. So whatever goes here, right, I'm just going to replace x with that value. So we have 7 minus 4, or 3. And now we have g of 1 times f of 4. So, okay, we're just going to do the same thing. We're going to plug 1 into the g function. So the g function is 3x squared minus 5. The f function is 7 minus 2x. So right now I'm just leaving some empty parentheses for those inputs. We're going to plug 1 into the g function. We're going to plug 4 into the f function. And now it's just order of operations. Let's evaluate this. So let's see, that's 3 minus 5, which is negative 2, times 7 minus 8, which is negative 1, and we get positive 2. We have So now we just plugged in some domain elements, right, to get outputs, but we could also plug in another expression into this function. You know, for all values x, 2x is always going to be a real number no matter what x is. So like, this will just tell me, like, as an expression, what do I get if I plug in 2x into the g function? Again, the g function is 3 times the square of the input minus 5. So this time that input is 2x. 2x all squared is 2x times 2x, which is 4x squared. Now we've got 12x squared minus 5. What this tells us is that if I took any real number, right, anything that I might plug in to the function x, if I double it first and then plug it in, that's the same as just squaring it, multiplying by 12, and subtracting 5. Okay. If we have a couple of functions and their domain and codomains are compatible with each other, then we could compose the functions together. So here's what I mean by compatible. So in this definition, g is a function that maps from a to b. I'm going to do a little sketch up here in the margin. So I've got 3 sets. I've got set A, set B, and set C. They tell us that G maps from A to B, and F maps from B to C. So what I mean when I say that if the domains and codomains are compatible, I'm mapping G maps into a set that is the domain of F, right? So F can kind of pick up where G leaves off. That's what I mean by compatible. If the domain and codomains are compatible, then the composition f of g is defined. F of g means when you read this as f of g, you always start on the inside and work your way out. So this means you apply g first, and then you work out and say then apply f to that. So we use that little circle, say f composed with g or f of g, but it means the same thing as this does, right? F of g of a. Okay, so figure out what g of a is, plug that into f. And this definition just says, look, if they're compatible, then we have this new function, f of g, that maps from A directly into C by way of B, really. So in example 4.6, we have these same functions. F is 7 minus 2x, g is 3x squared minus 5. And they both map reals to reals, which means the domain and codomain are compatible. In fact, they're compatible both ways, right? They both map from reals to reals. Each function can pick up where the other function leaves off. If we're going to find f of g, well, I'm going to find f of g of x. So what I'm going to do first is say, okay, this g of x here, I'm just going to replace with the expression for g of x, which is 3x squared minus 5. So I want f of 3x squared minus 5. And the f function is the one that says take 7 and subtract 2 times the input. And in this case, my input is 3x squared minus 5. We'll do a little algebra to simplify. So 7 minus 6x squared plus 10, or negative 6x squared plus 17. There is f of g of x. Before we do the next one, we'll just note, like, what this means is that if I wanted to find say f of g of, I don't know, 2. Normally, right, what I would think of is all right, I'm going to plug 2 into the g function, see what that gets me. So g of 2 is 3 times 2 squared minus 5, so that's 4, 12 minus 5 is 7, so this is f of 7, and f of 7 says take 7 minus 2 times 7, which is negative 7. So that's, you know, when I think about basically how to think of this composition by saying, okay, I've got a number 2, let me see where g sends it. It sends it to 7, and then f sends that to negative 7. What we're saying here, after that algebra that we did, is that this should be the same as taking negative 6 times 2 squared plus 17. So this is minus 6 times 4 plus 17. Minus 24 plus 17 is negative 7. And these check out. Let's try the other composition again, because they both map reals to reals, and then so we have compatibility between the domain and codomains going either way. We're going to find g of f, so g of f of x is g of, now the f function is 7 minus 2x. The g function is the one that says, what, that's a 3x squared minus 5, so 3 times the square of the input minus 5, and this time that input is 7 minus 2x. What do we have to do algebraically here to simplify? Foil, yeah. So we're going to foil this out. I'm going to make the little table here. So 49 minus 14x minus 14x plus 4x squared. So we get 4x squared 3 times 4x squared minus 28x plus 49 minus 5. And let's see, we'll distribute, so we get 12x squared minus, what's 28 times 3? I don't have my calculator, so I'll just use this one. What is it? 84? 84x. 49 times 3 is 147 minus 5, so 12x squared minus 84x plus 142. I won't do an extra example to show how it works, but that's the idea, right? The same thing that I did up there, finding f of g of 2, I could do the same thing here to find g of f of whatever, and I'll see that I get the same answer either way. What I want you to understand right now, look at what we got here, right? For these two. Any observations we can make here? G of f is what? Yep, for some values. I'm looking at something like a more general observation. So you said that G of f seems bigger. I'm going to just make a more general observation, I guess probably included in what you just said, but these are not the same, right? We got different functions. And what that means is that function composition is not commutative. Okay. So now we know what has to be true in order to have a function, right? We can't split our inputs, right? Once I've picked an input, there can only go to one output. But there are other properties that a function may have. There's two properties. One property is that a function could be onto or surjective, and a function could be one-to-one or injective. A function could be either or both or neither of these properties. So what onto means is that the range is equal to the codomain. That means everything in the codomain gets hit. It doesn't just map into a set, it maps onto the set, right? It covers everything. A function is one-to-one if, in the beginning of this section, when I was talking about, just what makes a function, and how, and I was talking about the snack machine, I was like, totally fine to have 2, 3, 4 rows of Doritos if you want, right? It is fine, it's still a function, but it wouldn't be one-to-one, right? A function, you can double up on outputs and still be a function, but you can't double up on outputs and be one-to-one. So a function is one-to-one, which means one input to one output. Like, once that output is taken by an input, it can't be hit by any other input. So that's what makes something one-to-one, and the way we kind of write it out kind of mathematically is that we say if f of a equals f of b, then a equals b. Like, the only way, like if you had a scenario where you had these two inputs that map to the same output, which is what f of a equals f of b means, right? I plug in a, I plug in b, I get the same thing. The only way that happens is if they were the same input in the first place, right? So when we think about the types of functions that we know and love that are, maybe map reals to reals, think about these graphs that we can make. The function on the left is one-to-one. Given any output, right? And outputs are the y-coordinates when you graph them. So given any output, there's only one x that's going to hit it, right? Like if we pick here, the one that they've picked on the figure is this value here. There's only one value, 5, that maps to oh, that's not 5, 4, that maps to 2, right? If I think of any output I want, there's only going to be one real number that maps to it. We could tell that if we're looking at a graph, we could tell a function is one-to-one if it passes what we call the horizontal line test. The graph on the right is not one-to-one because I can see that there are two values, both 4 and -4, will map to the output 2. We've doubled up on outputs. So the one on the left, this is one-to-one or injective. Each input maps to a different output. And this one is not one-to-one. 2 inputs map to the same output. In fact, that happens over and over again. There are infinitely many y values, right, y coordinates, where I could say, look, these two different values map to the same output. You only need to find one instance of that happening to show that a function's not one-to-one, right? But certainly in this case, we have many to pick from. Right, so if somebody gave me that that function, this g of x function here, and they said, show me, prove that it's not injective. Proving that it's not injective is simple. This is where I just need a counter example, right? We did some counter examples on the take-home test about showing that something was generally false. So all I would need to do is say, look, f of 2 is equal to f of -2, right? They're both 4, but 2 is not equal to -2, and that's it. So they gave us an example of a function that's one-to-one and one that's not one-to-one. Can we come up with a function that is one-to-one? think of a function, you know, like some mapping where different inputs have to go to different outputs, where it's impossible to double up on outputs. What? No, give me an actual function.
F of x equals 2x.
2x. Sure. In fact, anything linear,
Yeah.
any linear equation will work. Yep. How about one that's not one-to-one? Let's come up with a function where we could find two inputs that map to the same output.
To the absolute value, or f of x equals to absolute value of x.
Sure, yep.
One on either side.
Mm-hmm. Let's do another one. Well, just more, like we just, it's good to kind of just get ourselves thinking about, you know, so now we have a couple of examples that use absolute values, and we can sort of see visually. Think about that similar type of behavior where we can, you know, something that would fail the horizontal line test if we graphed it.
X squared.
X squared, yep. Any others? What's that?
Anything with an x polynomial x too much?
Well, x cubed is not is one to one. In fact, anything like x raised to an even power would be not one to one. Another one, if we think back to pre-calc 1 and pre-calc 2, like sine x, right? That's periodic, right? So it repeats. There's lots, right, of values. Another one-to-one function, call that f1, f2 of x. E to the x is one-to-one, right? So again, pre-calc 1, we did some stuff with exponential functions. We may occasionally be asked to prove that a function is injective. Proving that a function's not injective, remember, is simple. You just find a counterexample. You find an example of two different inputs that map to the same output. It's simple. You might have to like hunt around a little bit to find the counterexample, but then writing it up takes one line, all right? Proving that something is true is a little bit more involved, but we've got a nice we have a nice technique, and it really goes back to this definition. So this definition that says, if f of a equals f of b, then a equals b. That's what it means to be injective. So if a function is injective, if we're trying to prove that, what we want to do is say, well, let's suppose f of a is equal to f of b. See what that gets us. That'll get us some kind of equation, right, if we have an actual function that we're working with. Then if we can algebraically manipulate it and show that the only way that happens is if a is equal to b, then we're done. So this type of proof is, there's a little bit less, you know, it's a little less wordy than the other ones that we've done. But we're going to prove that 3x plus 5 is injective. We're probably not surprised that 3x plus 5 is injective. It is, after all, linear, and that was one family of functions that we just sort of observed. Oh, of course, this will be injective, right? So let's suppose that f of a is equal to f of b. Or you can use f of x and f of y if you like, but so that gets us an equation, right? F of a, I mean, they gave us a function. F of x is 3x plus 5. So f of a is 3a plus 5 is equal to f of b, which is 3b plus 5. Now let's observe. We can do some algebra. All right, we'll subtract 5 from both sides. As I'm doing the algebra, I am being on the lookout to make sure that there's no funny business, that I'm not assuming something that I'm not allowed to assume. In particular, think about like when we do some algebra to solve an equation, if I have to take the square root on both sides, like then I have to do the plus or minus. Like that's something to be on the lookout for. But like there's no ambiguity. Like subtract 5 from both sides, right? That's a regular old operation. It doesn't require us. That doesn't inject any ambiguity into the algebra here. Now I could divide by 3. Again, that's another, we say that that's an injective operation. That, if I take a real number and I divide it by 3, there's only one possible output I'm going to get, right? 1/3 of a particular number, there's only one value. There's no ambiguity in what I'm going to get. So if I divide by 3, then that forces us to conclude that A is equal to B. So look, we said suppose f of A is equal to f of B, and then we concluded that A is equal to B. And that's all we need to do to draw our conclusion. So since f of A equals f of B implies A equals B, then the function f of x equals 3x plus 5 is injective. How we doing? Okay, if a function is injective, then f has an inverse function. It has a going backwards function. I'm going to scroll back again to the first page real quick. So, here's sort of a generic picture of what a function does, right? We have inputs, it maps it over to outputs. F inverse, if the inverse function exists, just undoes that. It says, oh, if I know what mapped to this value over here, I have an inverse function that'll tell me what mapped to it in the first place under the f function, okay? Now, in order for an inverse to exist, our function has to be one-to-one. Because if you look what happens here, right, we had this scenario where both A2 and A3 map to this same output. So if this function, which now the way I've drawn it is not one-to-one, it doesn't have an inverse, because if I try to go backwards and say, okay, let me start with this value right here and send it back through the function, then there's ambiguity. Well, maybe it goes to A2 or maybe it goes to A3. Then that's obviously not a function. So if a function needs to be injective in order to have an inverse, if it has an inverse, often there's some algebra that we can do to find the inverse function. So again, we'll take that same linear function, 3x plus 5. And there's a pretty simple procedure, I guess simple depending on what type of function it is and how much algebra we might need to do. But basically, I start with this function, f of x equals 3x plus 5. First, I just write y instead of f of x. Then, so there's step one. Step two, I'm just going to swap x's and y's. So this is going to be x equals 3y plus 5. Now I'm going to do algebra and solve it for y. Alright, so subtract 5 and then divide by 3. So we get y equals x minus 5 over 3. So this part here is step 3, I guess. And then last, we just, instead of writing y equals, we write f inverse of x. That superscript -1 just indicates that it's an inverse. It is not an exponent. It does not mean 1 over f of x. Questions? Okay. All right. We can also show if a function is, okay, let me start over. Showing that a function is not surjective is usually pretty easy, right? You find some element in your codomain and you say, look, this can't get hit by any domain element, and here's why. For example, like f of x equals x squared. If I think of that as a function mapping reals to reals, I say, oh, not surjective, nothing maps to -1. There's no real number that maps to -1, right? And then I'm done. To show something is surjective, though, takes a little bit more work. So the way we do it is we say, let's let B be some random element in the codomain. We're not going to actually pick one. We're going to call it B or call it whatever letter you want. The only thing we're assuming about it is that it's an element of the codomain. We use a little algebra to find out what element A in the domain would map to it. Often this might be some side work. You know, it could appear in the body of your proof, or it could be kind of off to the side. It should be included regardless. And then just say, and then you show, look, here's this element A that I know is in my domain. Like, that's really important. You got to say, like, I know this has to be a domain element. And then you just say, look, I'm going to plug it into the function, and that gives me B. So we're going to work with the same function, 3x plus 5, show that it's surjective. Again, we said it's not so surprising that the linear functions are injective. It's also not that surprising that they're surjective, right? It's a line, right? So no matter what y coordinate I pick, eventually I can find an x coordinate that will get me there. So we're going to let B be a real number, and I'm letting B be a real number because that's the codomain. We will find an element A in the domain such that f of A equals B. A being in the reals because that is the domain. Right, the domain and the codomain happen to be the same here, but so I'm really taking my time and emphasizing that B is an element in the codomain. That's the only thing we assume about B, and we have to make sure that the element A we find that maps to it is an element of the domain. Anybody need to? Oh, is that Ahmed's? He's not here. Okay. Well. Okay. It'll stop eventually. Oh, it's Ali. Okay. All right, so we're going to find an element, A, such that f of A is equal to B. So if such an element exists, then we have f of A, which is 3A plus 5, equals B. Here's the equation, right? Now we have an equation. Let's do the algebra and solve for A. Yeah. Oh, ha, thank you. There we go. Now let's do some algebra. Let's subtract 5. Really, same kind of algebra that we did on the last page. And then we divide by 3. A is equal to B minus 5 over 3. So there's a couple things we want to do now. It seems like we're pretty close, right? We seem to have found what element A has to be. So because B is a real number, right? That was what we assumed. Then B minus 5 over 3 is a real number, right? If I take a real number and subtract 5, I know it's a real number. If I take a real number and I divide by 3, I know it's a real number. So A is an element of the domain. Now observe. This is the last thing we're going to do. F of A. We're going to find F of A and show that it maps to B. Right? We picked an element B, a random element B in the reals. We found this element B. This is our assertion. This is our hunch. We say, we think this is the guy right here. B minus 5 over 3. So now we're just going to show that it maps to B. So F of A is F of B minus 5 over 3. And the F function is 3x plus 5, so it's 3 times B minus 5 over 3 plus 5. We do some algebra. The 3's cancel here. We have B minus 5 plus 5, which is, of course, B. And this tells us that f of x equals 3x plus 5 is surjective. Functions could, the 3x plus 5, that function is both injective and surjective. A function could be one but not the other. For example, e to the x, that exponent or any exponential function is injective but not surjective, right? E to the x, if you look at a graph of e to the x, then let's see. I'll come back to this in just a second. But if I look at a graph of e to the x, it looks like this. Definitely passes the horizontal line test, but it's not surjective because I can't, raise e to any power and get a negative. So there are functions that have one but not the other. There are functions that have neither property. So for example, if I think about, so this was reals to reals, x goes to e to the x. We could also have our function g from reals to reals by x mapping to x squared. This has neither property, right? We've already observed that it's not injective because it definitely fails the horizontal line test, and we've observed that it's not surjective because nothing maps to -1. If I sort of artificially change the codomain and say, oh, I'm just going to map from reals into the non-negative reals, then all of a sudden it's surjective because I've just sort of restricted that codomain. I want to kind of finish up by looking at some special functions, the floor and ceiling functions. So the floor function, which is also called the greatest integer function, both of these functions map from reals to integers. So the domain, you can plug in any real number, it'll only spit out an integer. The floor function is the greatest integer less than or equal to x. The ceiling function is the least integer greater than or equal to x. So like the floor function is like a rounding down function, and the ceiling function is like a rounding up function. So for example, if I apply the floor function to 2.7, I just get 2. It's like take the integer part. If it's a positive that you plug in, it's like just take the integer part. If it's a negative, you got to be careful because you're rounding down. But if we apply the ceiling function at 2.7, it gives me 3. That's the smallest integer that is greater than or equal to 2.7. So the floor function is sometimes called the integer part. If I take a real number and subtract the integer part, we just get the fractional part. So here's a way that you can say, just give me the fraction part. Give me the stuff to the right of the decimal point. You sort of construct that with an input by using the floor function. We should note that neither of these functions is multiplicative or additive. And here's what that means. If it's not additive, that means that if I take the floor of x plus the floor of y, This is, in general, not equal to the floor of x plus y. I'm not saying that you can't find instances where equality holds, but what I am saying is there's plenty of times when equality does not hold. And the same is true for the ceiling. And then they're not multiplicative either, so the floor of x times the floor of y is in general not equal to the floor of x times y. Same goes for the ceiling. And one nice application of the floor function is how we build the mod function. So let's look at an example. We're going to calculate the floor of 17 divided by 5. So if you take 17, you divide it by 5, you get 3.4. And if I apply the floor function to that, we get just 3. And really what that does is it tells me how many times 5 goes into 17, right? What whole number of times, right? Ignoring the remainder, right? So I could take 5 out of 17 3 times, and then I have a little bit left over, but not enough to take it out again. We would say that it gives us the quotient upon dividing 17 by 5, right? So the floor of n over m is the quotient upon dividing n by m. Now what we want to do when we make the mod function is, the quotient is nice and all, but actually what we're more interested in is what's left over. After you take out however many times, right? If I take 5 out 3 times, how much is left over? What's that? Well, the 0.4, but how many, like, so think of it as the integers, right? I start with 17, I take 5 out 3 times, how many is left? 2. That's kind of that remainder is what we're interested in. That's what the mod function does for us. And we can build the mod function using the floor function. So what we do is we take, the floor of n over m tells us the quotient upon doing the division. So I take that and I multiply it by m and subtract it from n, and that gives us n mod m. So we can calculate 17 mod 5. And we're going to do it by using the floor function here. And eventually we're going to do it so much that we're not even going to think floor function when we do this. But it's sort of an interesting way that we can actually build new functions from old ones that we have. But 17 mod 5. So this says I'm going to take 17, subtract 17 over the floor of 17 over 5 times 5. So the floor of 17 over 5 we said was 3. And that gives us 2. That's what's left over. This is the remainder when we divide 17 by 5. So thinking about it in terms of remainders is usually like the quickest way to see what we get. We have to be careful though. You have to be careful when we are working with negative numbers in particular. So we're going to do 2 extra little examples here. We're going to find 43. So I'll call this 4.13b and 4.13c. So we're going to find 43 mod 8. This says, or the definition above says I'm going to take 43, I'm going to subtract, I'm going to take 43 over 8 and apply the floor to that, and then multiply that by 8 and do the subtraction. How many times does 8 go into 43?
5 times.
5 times, okay. So that's what we get when we take the floor of that. So we have 43 minus 5 times 8, and that is 3, yep. So that's 43 mod 8. And that makes sense, right? It's the remainder when I take 43 and divide it by 8. 4.13 part C. Let's find negative 43 mod 8. So this says I'm going to take negative 43. I'm going to subtract negative 43 over 8. Apply the floor function to that times 8. Now if I do the division here, that'll give me 5.375, negative 5.375. If I apply the floor to negative 5.375, what do I get?
Negative 6.
Negative 6, great. So I've got negative 43, that'll end up being plus 48, which is positive 5. We have to be a little bit careful. It's harder when we do negative 43 mod 8 to just think of it as a remainder upon division by 8, right? It works, that type of thinking works great when it's positive. Now, think about all the remainders you can get when you divide something by 8. We're almost done here. What are the remainders you can get when you divide something by 8? Say that. 1 through 7. You're very close. You're missing 1.
0.
Yeah. Right, something could be a multiple of 8. Okay. So when we did 43 mod 8, we got 3. When we did negative 43 mod 8, we got 5. Now, so if something leaves a remainder of 7, when we divide it by 8, that means it was 7 more than a multiple of 8. That means it's also 1 less than a multiple of 8, right? So I could really think of the 7 as the same thing as a negative 1. If something leaves a remainder of 6, that means it's 6 more than a multiple of 8. That's the same as being 2 less than a multiple of 8. And if something is 5 more than a multiple of 8, that means it's 3 less than a multiple of 8. So it's harder to think of it in terms of remainders when we're working with negatives. However, if I know that 43 mod 8 is equal to 3, negative 43 mod 8 is in fact equal to negative 3. It's just that that's not what when we express something mod 8, we always give it as a remainder, a positive number. We're going to do a lot more with this in like chapter 5 and 6, but these weren't inconsistent, right? It wasn't that we couldn't think of it in terms of remainders, but we just had to go the extra step and say, oh, that's a negative 3. Negative 3 mod 8 is the same as 5. How we doing?
Much prefer after the cell.
Good. We're going to do a lot of it. I'm going to remind you that you said this later when we're doing some stuff. I'm going to. Yeah, in fact, I'm going to bring up the recording. I'm going to get it ready. I'm going to have a sample ready so that when I hear, like, if you're like, oh, this is too hard, I'm just be like, bam, and then I'm going to play it and everybody can remember. Yeah, yeah, yeah. All right, thanks, everybody. I will see you all on Thursday.